Okay, so we are going to talk a little bit more about probability, a few unique, different, a little bit more confusing probability situations. So the first one that we're going to talk about is the probability for the union of two events. And so what that means is you're trying to figure out the probability that this or that could happen. So you have to remember that the union, the way we symbolize union is with a big U, and the way we symbolize intersection is with an upside down U. So hopefully that you remember that from previous math classes. So we have a formula to figure out the union, the probability of the union of two events, and that is to take the probability of A, add it to the probability of B, and then subtract the probability of A and B happening at the same time. So what's interesting is that sometimes A and B happening, it never happens. Okay, so there's never any intersection between the two sets of A and B. And so what we call that is we call those things mutually exclusive. And so when that happens, your probability of A or B is just the probability of A plus the probability of B. And you probably remember me mentioning that when you use the word or, we like to add, and when you use the word and, we used multiplication, right? That was from our counting principle. Okay, so it's going to kind of follow along that, kind of feel that way. So let's do an example here. The following data was collected from a finite math class at State University. So we've got freshmen, sophomores, and juniors, and we have students that have a scholarship, and we have some students that do not have a scholarship. So there are a total of 34 students in the table above, and we're going to pick a student at random from these 34 students. We want to find the probability that the student is a freshman or a sophomore. So that's going to be this union of the two events, probability of A or B. So first of all, think of the event A as being the student is a freshman, and the event B is that the student is a sophomore. So if we plug that into our formula, the probability of A or B, we take the probability that the person is a freshman. So we look and see there are a total of 13 freshmen. So 13 out of 34 is that probability. And then we need to take the probability that the student is a sophomore. So we look at the sophomore row here, and there's a total of 12 sophomores. So 12 out of 34. And then we have to subtract the probability that the person is a freshman and a sophomore. Well, you're one or the other, you're not both, so that is a 0% chance, right? A 0 out of 34 probability. So it looks like these events are mutually exclusive. So all we have to do is add these two together to get our probability, which is 25 out of 34. So that's not too bad. Let's look at question number B. It says, what is the probability that the student chosen is a junior and has no scholarship? Okay, so this right here is an intersection, that the probability that the person is a junior and has no scholarship. So what we're looking is, here is the row for juniors, and here is the column for no scholarships. So there are only 6 juniors that have no scholarship. So the probability of picking one of those people is 6 out of 34, which we can reduce to 3 out of 17. So just because it had the and in there, the intersection, doesn't necessarily mean that we are going to multiply. We just have to look at this table and figure it out. Next, what is the probability that the student is a junior or has no scholarship? Okay, so now we are looking at the event A being the junior, and the event B is that they have no scholarship. So the probability of a junior or no scholarship, we're going to take the probability that they're a junior. Well, it looks like there are 9 juniors, so 9 out of 34. We add that to the probability that they do not have a scholarship. Well, we look over here, it's going to be all of these people that have scholarships. Okay, so, or I'm sorry, the ones that do not have a scholarship, my bad. These ones right here. So we add those up, there's 18 of them. 18 students that have no scholarship. And then we subtract the students that are juniors and that have no scholarship. And we figured that out before, is 6. So we do 9 plus 18 minus 6 to give us the 21 out of 34. So what we could have done, if you thought about it, especially when you have this table, we're looking at finding all of the students that are juniors or that have no scholarships. So you're looking at this number, this number, this number, and this number. And of course, we're not going to count 6 twice, right? So that's kind of where you can think of subtracting this 6 as if you had counted them twice, I suppose. If you did all of these and all of those, you counted it twice. Okay, so that's great. If you have a table, you can look at that information, plug it into your formula, and be on your way. So let's look at a different kind of probability. What if we have this probability where we are supposed to figure out the probability of the union or intersection of these events happening, and we have given to us already these probabilities. So it's not an actual situation, it's not a table, we don't even know what these stand for. We just know that the probability of A is 0.6, the probability of B is 0.3, and the intersection, the probability of the intersection of A and B is going to be 0.1. So if you notice, I have already drawn a Venn diagram, and what we're going to do is we're going to put the probabilities in all of these spots accordingly. So the first probability that you want to fill in is this intersection, A and B, which they've already given us is 0.1. Then we're going to go over here to the probability of A, which they've told us this whole circle should be 0.6. Well, we already have 0.1 of that 0.6 taken up in this intersection. So the remaining part right here is going to be 0.6 minus the 0.1, so that's going to be 0.5. So if you see, the 0.5 plus the 0.1 should give us the 0.6 for the probability of A. We can do the same process for B. Since the whole probability of B is 0.3 and this is 0.1, we know that the remaining part has to be 0.2. Now, if you wanted to get really fancy about things, we could think about the probability that it's out here, that it's in neither A nor B at all. And so if we know the total probability would have to be 1 of it either happening or not happening, we add all these up together and subtract from 1. So this is 0.8 altogether. That means that the remaining probability would have to be 0.2, sorry. All right, so we can use this table or this Venn diagram now to help us figure out this probability. So the first one, the probability of A or B, we're going to take the probability of A plus the probability of B and subtract the probability of A and B. And that comes out to be 0.8. And that should make sense because it's either here or there or where they intersect each other. And that whole thing is 0.8. Okay, next one. Find the probability of A and not B. Now this one is a little bit more complicated to figure out. The probability of A and not B. So that means it has to be in circle A, but at the same time it cannot be in circle B. So that means we just want this area right here, which is the 0.5. All right, and then the third one, find the probability of not A or B. So once again, we're going to go back to our formula, probability of not A or B. So we take the probability of not A. Well, if probability of A is 0.6, not A is 1 minus that, so that would be 0.4. The probability of B, well, they gave us that as 0.3. And then we have to subtract the probability of not A and B. So we want it to be in B, but not in A. So that's going to be this 0.2, because it's over here in B, but not in A. So we add that all together and we get 0.5. Okay, so this Venn diagram can be very useful. You probably could do it without it, but I find it to be very helpful. All right, let's take a look at our last type of probability, and that is conditional probability. A conditional probability is the probability that an event will happen given that a second event has already happened. So we say the probability of A given B. And we have a formula to figure that out. You're going to take the probability of A and B together and divide it by the probability of B. So sometimes it's easier to think of it with the formula, and sometimes it's just easier to think about it like what is actually happening. So for this example where it says what's the probability that a king is drawn given that the card is a heart? Well, let's use our formula first of all. So the probability of a king given a heart, we're going to figure out the probability of a king and a heart. Well, there's only one card in that deck that is the king of hearts, so that's a 1 out of 52 probability. That's going to go on top. On the bottom, we're looking at the probability of a heart. Well, there's 13 hearts in the deck, so 13 out of 52. And so you notice that these 52s are going to cancel each other out, and we left with a 1 out of 13. But the other way of thinking of this is, what's the probability that a king is drawn given that the card is a heart? It's like somebody's drawn a card from your deck of cards, told you that it's a heart, and now they want you to figure out if it's a king or not. What's the probability? Well, if you already know it's a heart, you already have limited the pile to choose from down to 13 from 52. So you could just directly figure it out. It's 1 out of 13. So sometimes that might be easier to think about. We can also do this kind of probability using a table. So once again, if we look at this table, we have male and female employees, and some, or I guess just a group of people. Some are employed and some are unemployed. Okay, so what is the probability that if a person is selected at random from the table above, that the person is employed, given that the person is male? Okay, well, the way that I think about this here is, instead of using that formula, we can say if we know that the person is male, let's look at, here are the males. There are 550 males. And we want the probability that that person is going to be employed. Well, there's 500 of them out of that 550. So there's your probability, 10 out of 11. We can do the same thing. What is the probability the person is female given that the person is employed? Okay, so we need to first figure out where are the employed people. Here they are. There's 700 of them. And we want to say, what's the probability that the person is female? Well, there's only 200 out of those 700, so our probability would be 2 out of 7. All right, well, I think I've given you enough to think about here. You guys can go off and do a lot of practice, and hopefully you'll get really good at it. Good luck!